So today we've seen really extremely exciting and fascinating robotic projects. So I knew about most of them, but it was really great for me to see the details and how they're actually done. But in my presentation, I want to go a bit of a different route. So not so much look at the high end, but look at how you can actually bring robotics to your projects. Maybe without having a huge company, a huge team, or huge funding at your back. So yeah, as was announced, my name is Johannes. So I'm one of the founders of the Association for Robots and Architecture, together with my colleague Sigrid Brell. I'm also a university professor in Austria, and I'm the main developer of Cougar PRC, a software that runs in the visual programming environment, now also Autodesk Dynamo, which we're going to see today. Yeah, so when I think about Autodesk University, a big difference compared to Google I/O, Adobe Max, or Microsoft Build is really that we think about how we can bring our designs, how we can bring our projects from the digital realm into the physical realm. And so programs support us with that. And sometimes the execution of our plans is done by hand, like for example, still at many construction sites. But of course, it's getting more and more important to use machines to automate these processes, as we've also seen in the keynote. And there's software to support us with these processes. So if you want to do milling, there's software that can calculate the tool paths for you. If you want to do 3D printing, then there's also software that's going to support you in preparing data for 3D printing. But what do you do if you want to 3D print not in a small scale, but if you want to bring 3D printing in a really huge scale? Could you do if you want to produce very complex formwork, hundreds of freeform pieces in an efficient manner to realize complex freeform structures? Or what if your plan is actually that you want to do spatial 3D knitting, but you don't work for Adidas, you don't work for Nike? Or maybe you want to take just simple ropes and turn it into a structure. Or you want to think about how you can translate digital experiences and kind of make them affect the physical environment as well. Or if you think about new things, how would it be possible to 3D print liquid within liquid? Or maybe think about new ways of structuring stone. Or, I promise that's the last one, maybe deform acrylic glass without using heat. Well, the basic and very simplified answer for all of these projects is that you're probably going to need 3 people for that. You're going to need one person who knows about the process, knows how to do it, and let's call him or her the designer. Then you're probably going to need an engineer who's going to build your machine. And lastly, you're going to need a programmer who's going to program that machine. And of course, doing so poses quite a high barrier of entry, because you're going to need a team, you're going to need expertise, and this is sometimes hard to come by. As that's the topic of this session, of course, you won't be astonished when, as the solution for the machine part, I want to present to you robotic arms. We've seen them before, you know them from the automotive industry. And because you have to know that even for high-end customers, it's not really fun to design a custom machine for new 3D printing, a custom machine for stone processing or whatever. So building machines is complicated, it's expensive, and even the automotive industry with all the budget, they like to use machines that, like robotic arms, that are basically universal machines. So you can equip them with any range of tools, and that tool then turns them into a milling machine, turns them into a welding machine, or anything else that you can actually think of. So for us, this is a very big advantage. At the same time, they can work in a very large space. So that's also a change. If you think about 3D printing in general, you have a machine that's about that size, and then you can 3D print something like that size. So robots open it up much more, and that's probably also one of the reasons, if you saw the metal 3D printing projects before, that they're actually using robotic arms for that. And this is also important because we're experimenting, we're testing out new things, new processes, and sometimes accidents happen. And robotic arms are really robust. They're really made to be working 24 hours a day for many years, and if something like this happens, it usually doesn't mean that you have to change your robot, bring it to service, whatever. Hopefully, just like in this case, it's going to keep on working. And of course, we're talking about bringing robots to SMEs, to also smaller companies, so price is a very big factor. And compared to many other machines, there's actually a used market for robots. So robots are not that expensive for larger companies. So it makes sense for them to get rid of old machines before they actually break down. So they rather don't take any chances, get a new robot. So those machines then actually end up on the used market. So today you can just go on eBay, you search for KUKA robot, and you can find one for $4,000. I wouldn't necessarily recommend that one, but starting at 10,000 euros, there's actually going to be decent machines. So that's about the machine or the engineering part. But robots have been around for many decades now, and there's a reason why we're only now starting to see these really exciting projects popping up that show us what can be done beyond just automotive fabrication. And a big part of that is software. So that's just a sample workflow that shows you how do you get, if you want to use a robot for milling, how you have to do that. So you start drawing your geometry in CAD, let's say in Inventor, in Fusion, whatever. Then you export it to the milling software. From the milling software, you export it to the robot simulation environment, and then you send the data to the robot. So on the one hand, all of these software environments are very expensive. So if you add it up, you're probably looking at like 30,000 euros just for the software, which is about half the price of a completely new robot, or the price of 3 used robots, if you want to put it like that. On the other hand, these are all separate software packages. So if you find out that the robot cannot reach a point, you have to go back, you have to change it, and then you have to redo it. So all of this is now getting better also in commercial software, so that's important to say. And if you're an expert in robot milling, that's not a problem for you, because you have a feeling, you know how the robot moves, how it behaves. You can kind of anticipate when you do the milling strategy if the robot will be able to reach that. But that doesn't really apply if you're not an expert. So for us, this was an idea, it was the kind of reason to look into visual programming as a way that we don't solve this kind of process sequentially, one after another, but that we actually try to be able to solve them at the same time. So in this case, that we have the fabrication and the design in one environment, and if we change anything at the beginning, we see immediately how it's going to affect the robot at the end. So our software for that is called KUKA PLC, standing for Parametric Robot Control, and it's now also running in Autodesk Dynamo. And it's looking a bit like this. So this is like the simplest possible example. So you draw a curve in your CAD environment, in this case in Revit, and then you kind of reference it in your visual programming. You divide it into a number of points, or actually then coordinate systems, and then you constrain it basically to the robot. So now, whenever you do anything, you see how the robot can fabricate it, or if the robot cannot reach a point. And if you do any changes to the geometry, the robot is going to react immediately to it, and you can get this kind of intuitive feeling for the machine. So you don't have to become a robot expert to do that, but you can actually just interact with your very flexible parametric model. You see what works, what doesn't work, and then you can kind of learn from that. Think of it a little bit like digital photography. You take a photo, you see if it worked, if it didn't work, you can react according to it. And the software then supports you with this kind of process. We can, of course, still do these kinds of workflows that we've seen before, that we load a G-code, we then turn it into robot movements. So this is still entirely possible with visual programming. But of course, the interesting thing is when we actually link the data, the simulation of the robot, also with flexible data. So in that case, again, just a very simple example. We have our freeform surface, and it consists of several elements that all look somehow the same, but actually every element is different. So in that case, we can then automatically extract these elements and also automatically generate the data for the robot to actually fabricate that piece. And this is for us very valuable because we don't have to expose people to the entire complexity of a robotic process. With visual programming, they have this kind of nodes, and they only need to understand what's the data that's coming in, what's the data that's coming out, but they don't necessarily have to understand what's actually happening inside. They don't need to know how to simulate a robot because that's happening internally anyway. So processes like this in a large scale are, for example, used for large-scale timber manufacturing, what you saw before. So you see we have this kind of wooden formwork for free-formed columns, and all of these elements, they somehow look the same, but again, each one is individual. If you do this with a normal workflow, you have to treat every element as an individual shape, and it takes up much time. But if you think about it more cleverly, you think, well, actually I only have to program it once, and then the parametric model is going to adapt accordingly. So it's not much more effort if we do it once, or if we do it like 500 times. And we can then also start thinking about putting in additional constraints. So if you mill stone, for example, you're going to have different challenges than if you mill metal, which is what most CAM software is actually optimized for. You can also then think about creating your own milling strategies. Like here, a very simple example that constrains the tool path to a raster image. But what's important for all of these kind of things is that you need to know about the process. So you cannot start from nothing. So if you want to do the knitting like we've seen before, it's actually important that you know how to knit in order to be able to program that with the robot. But this is a research project that we did like 1 year ago approximately. It finished. It was about stone structuring. So we worked with a stone company, and they had the issue that masons are very hard to come by in Germany. And one of the main businesses they have is not just this kind of sculptural work, but they have these panels of stone and they need to structure, to chisel them. And this is something where you need people who know what they're doing. You cannot just take any worker from the street, hand them a chisel, and they do it. But at the same time, it's very repetitive, it's not healthy, and people don't really like to do that. So in this case, we then actually first had to get the understanding how the process actually works. So before we could think about programming or automating that, we actually had to analyze it. So in this case, this was done with TU Dortmund. We actually put force sensors underneath the stone, 3D high-speed cameras in front of it, to actually get a feeling how this kind of structuring process then actually works, so that we could then start thinking about developing hardware for the robot on one side to do this operation, but on the other hand, of course, also to develop software. So we started out very simple with a soft material. The first tool that was developed by Labo in Italy was for actually manual winding up. So it was a fitness studio and research project at the same time. And then at some point, we had this electromagnetically actuated tool. But of course, there's no commercial software for structuring, for stone structuring. So this was our part in this research project, that we looked into how we can make this accessible, how we can actually simulate these kind of processes so that the people get this kind of immediate feedback. Of course, it's not only about taking processes that already exist manually, but to also think about how you can go beyond. So that's a company, Branch Technology, based in Tennessee, and they developed a large-scale 3D printing process. Not as a university, as a research project, but as a company, actually coming from architects who saw the need for large-scale formwork and then started getting a robot and then also getting our software for visual programming to actually be able to create these kind of structures. And as you saw before, they're now really scaling up production, and it's no longer just about building actually here, they're also thinking a bit further on. So this is a project they did with Foster, a British architecture firm, where they then started thinking about how can we use 3D printing also on Mars, for example. They made some prototypes and then actually won of the Mars Habitat Awards. And if you remember the 3D sequence you saw before with this kind of computer game flying through, so maybe you didn't think it was completely so thrilling, but I can promise you it gets thrilling if you're not just looking through 3D glasses, but you actually combine the movement of the robot with the movement you're experiencing in your 3D glasses and VR environment. That's a company called See It. And they again used the robot program environment to create these toolpaths and then synchronize them with their virtual reality experience. That's another project I'm very fond of. A That's from one of my previous students who now actually founded his own startup company. It's called Print-a-Shrink, and he developed the first process to 3D print liquid into liquid. And here it's not so much only about physical fabrication, but it's actually also very much about the fabrication as an event, as a marketing tool. So he's now very successfully selling this to companies who then offer customized cocktails at corporate events, and was really able to create his own business out of a very simple idea. Just to finish up, because I'm already a bit over time actually, for us, the kind of next thing we're now looking towards together with Autodesk is using Forge to creating web interfaces as a way to reach the end consumer. Because basically visual programming is accessible for us as designers, as architects, but not, of course, for the end user. So we managed to bring our entire robot simulation library into the cloud and use then Forge to visualize it. So people can, with a very reduced control set, create their own processes, and we can also check the feasibility of construction. So the things we have seen today not only apply to this kind of large-scale fabrication or high-end companies, but really also to smaller companies that buy used robots and basically mostly consist of a Facebook site, and they now have plans to fabricate their own boats out of using robotic arms. So for us, this is really exciting. It's very important to remember, and I have to emphasize it, that we are standing on the shoulders of engineers, of computer scientists. So all of this is only possible because we can build upon these technologies and also enhance upon them. But robots, I think, really offer SMEs the possibility to create entirely new processes and actually enable them to compete also with larger corporations. Because with lean workflows and very short design cycles, you can really, in a very short time, create entirely new products that you haven't seen before and much more directly also engage with your customer and with your audience. So I would just close with giving you all my contact details. So you're very welcome to get in touch, maybe now, maybe via email. And if you look for my other class that I taught at AU, you can actually already now download the software for Autodesk Dynamo. So it's available online. You can also get some instructions to do that. And we're very much looking forward to getting feedback from you as the user, because for us, Dynamo and then Revit is also a new environment, and we're very much looking forward to seeing how you're going to apply robots. Thank you very much. I'm sorry for taking a bit longer.